Okay, so the big theorem called the fundamental theorem of calculus. Sometimes it's known as the first fundamental theorem of calculus because we're going to see also another one. But this by far is the most important, the most famous one, and it's going to make our life easy. It's going to help us find those areas under the curves in a much more efficient manner. Now, it's going to take us a few steps to get to the theorem, so please bear with me. I'm going to first start by reviewing what we know so far. So let's say that we have a function f of x over the interval from a to b. And let's assume our function is positive, meaning that it's above the x-axis. So we've already looked at how we find the exact area under that curve. We first try to fit in n rectangles under that curve, right? So if the curve is given by that red function, the red curve, first we try to put n rectangles under it. What was the base of each rectangle? We call it delta x, right, which is the length of the interval b minus a over n. And then we write down the partition points. For the partition points, you start with the left end point a, and then you keep adding multiples of delta x to get, from one to the next partition point. And to find the area, you basically sum the areas of n rectangles. And in each case, this was the base, right? And this was the height of the rectangles because we plug the point into the function to get the height. So this is what we know so far. And we actually know one more thing. What was the exact area under this curve? We need to take a limit, right? To find the exact area, you take a limit as n goes to infinity of the above. So what you see right here is going to be the exact area. So this is the definition of the area under a curve. Limit as n goes to infinity, summation I goes from 1 to n, f of x sub I times delta x, a very complicated looking expression. So I guess mathematicians realize this is a very cumbersome notation, and they try to simplify it by choosing another notation. So to replace the first two things, to replace the limits and the sum, which is a lot of cumbersome notation as you see there, they decided to use an elongated S notation, which is something like this. So I guess from the Latin word like sum or summa or something like that. So they decide, okay, when you have an infinite sum, we're going to represent it by an elongated S. Okay? So from now on then, for area under a curve for a positive function, we're just going to use this notation. So exact area equals, and it's equal by this new notation that we're seeing. Instead of the limit of a sum, we're using the elongated S. And notice that on that S, you can also put the left end point of your interval and the right end point of your interval. So this represents, we're going to find the area from A to B. And you see in there, in our definition up there, we had f of x sub I times delta x. In this new notation, you see how that shows up itself? F of x sub I shows up as f of x. Again, they're trying to simplify the notation even further. And delta x, how did that show up? As just dx. You see, it's really the same thing in a sense. So f of x represents the height of each interval, dx represents the width of each interval, and the elongated s represents the summation of those areas in the limiting case as n goes to infinity. So all of a sudden, we have a much simpler looking notation. Okay. But it still didn't tell us, how do you evaluate this? All we know is, okay, it's simpler notation, but how do you calculate this in a simpler way? That has not been answered yet, which we're going to try to do in the next slide. But let me just tell you this much. This works for positive functions, right? The graph has to be above the x-axis. But if it is below the x-axis, there's a very easy fix. You take the absolute value of the result, basically, because there the heights are negative. If you want area, you convert the negatives into positives. You can still find area with similar methods. OK, now let's take a look at the statement of the fundamental theorem. OK, so let's suppose that we have a function here. This red curve is y equals to v of t, the velocity function. So an object is moving, and we know its velocity at any given time t, where t is in hours. I think I'm going to fix this just a little bit. Make that 50 up there. OK. OK, the first thing I'm going to ask you guys from this graph, Again, my goal right now is instead of just stating what the fundamental theorem of calculus is, which is very easy to do, I'm going to try to give you some idea behind, how could Newton and Leibniz have come up with this great, fantastic theorem? What could they be thinking? So we're going to try to derive it ourselves in the next 5 minutes or so. So in that end, we're looking at a specific function, not just y equals f of x, but the velocity function. And for the velocity function, I want us to think about what does the area under the curve represent for the velocity function? Because think about it, Newton was also a physicist, so it's quite possible he was dealing with the velocity function. He looked at the velocities of objects, falling apple, planets. So what would the area under this curve represent? Well, I did 2 rectangles there. You could put, of course, more rectangles. First, let's go 1 rectangle at a time. What is the area of the first rectangle? The base is how many units? The base is 1. And the height is, assume it's like right at 60. So the height is 60. So that's the area of the first rectangle. What is the area of the second rectangle? The base is 1 and the height is 50. And think about what the units are here, okay? On the base is time. So you have like 1 hour. On the y-axis, you have miles per hour, the velocity at which this object is going. It's accelerating, it's decelerating, it's going faster. But between 1 and 2 hours, it went at 60 miles per hour, right? So if I multiply those 2 quantities, what will I get? I get the total distance traveled in 1 hour, correct? And what is that total distance traveled in 1 hour? It was 60 miles. This object traveled 60 miles, although this is just an approximation because this object was not traveling at 60 miles an hour the entire 1 hour, right? Because if you look at the graph, it keeps changing, right? It keeps changing. Like first it was maybe at 40 something, then it was a little bit faster, then it was a little bit faster. But we assumed in that time interval from 0 to 1 hour, it's going to travel at a constant of 60 miles per hour. Obviously, this is not going to give us the exact answer, but the thinner your rectangles, the more accurate you're going to be in estimating the entire area, right? So again, finding the exact area under this curve will give us the exact distance traveled by that object over that time interval. So what are we getting then? We're getting 110, right? So what does this 110 represent once again? Total distance traveled from where to where? From the first hour to the third hour. So total distance traveled. And one way to represent that would be like this. Remember our S of t function, which represents distance traveled, the total distance traveled up to a point t. So I can represent it like this. S of 3, this is miles traveled in 2 hours, from the first hour to the third hour. I can represent it like this. S of 3 minus S of 1. Again, if S of t represents the total distance traveled within t hours, so if I know, let's say this object is going, from here to Jacksonville, and you're trying to say, okay, how much did this object travel between the first and the third hours? So if you know where this object was, how many total miles it traveled by the end of the third hour, maybe this object traveled, let's say, 200 miles by the end of the third hour, right? And if you also know where this object was by the end of the first hour, let's say that was, it was 90 miles was traveled at the end of the first hour. So how much was traveled between the third hour, between the first and the third hour? So you say 200 miles minus 90 miles, that would be like 110 miles, right? So in other words, S of 3 minus S of 1 gives us the total distance traveled between the first hour and the third hour. Now, another way to write S of 3 minus S of 1 okay, I want to see. Okay, I think I'm going to get back to that in a little bit. But right now, let's then try to do the following. Let's get to the next line. The integral from 1 to 3 of v of t dt. Remember now, what does this represent? The area under the v of t curve from 1 to 3. And based on what we just found, what is that area equal to? correct. And remember, we just learned this notation. Let's review the notation. The notation, if you have like f of x dx, that gives you the area under f of x from a to b, right? In this case, you have integral of v of t dt. That should be the area under the v of t curve, the velocity curve from 1 to 3. And what do we get for that? We just got that, right? What was the area under that from 1 to 3 hours? 110 miles. And one way to write that, we agreed, is the displacement, s of 3 minus s of 1. Distance traveled up to the 3rd hour minus distance traveled up to the 1st hour. That difference is the total distance traveled between the 1st and the 3rd hours, right? Okay. Now, I'm going to write this in one other notation for you. Would you agree that velocity is the first derivative of distance? We've seen it a long time ago, right? S prime of t is the same thing as velocity, because S prime is the rate of change of distance, right? That's velocity. Okay, so instead of v of t in this next line, look what I'm putting down. Instead of velocity, I'm putting down S prime. Can I do that? In other words, is velocity the same exact thing as S prime? It is, right? Remember, this was like when we did the applications of derivatives. The rate of change of distance was velocity, remember? ds dt or s prime was velocity. So this is a legitimate substitution then. I can replace velocity by the derivative of the distance function. They're the same things, right? Velocity is the same as s prime. Everybody agrees with that? Okay. So let me write the answer once again. So if you're integrating s prime of t, the answer turns out to be s of 3 minus s of 1, based on the graph that we've just seen. Now let's try to do the next one. The next one, I say forget about the distance function right now. Mathematicians, they don't like to put themselves in a small box saying we're only going to deal with the distance. They want to generalize things like y equals f of x. It could be any type of function, whether it's representing blood flow or whether it's representing flow of traffic from an intersection point. It's the rate of change of something you have, f prime of x right there. Based on the example above, what do you think the answer will be for any function f of x? We don't have just distance function right now. If you were integrating s prime of t, answer was s of 3 minus s of 1. If you're integrating f prime of x in general, what do you think the answer will be? Following the same exact pattern. Would everybody agree? F of 3 minus f of 1. Would everybody agree? What's the pattern that we observed here? If you have the derivative of the function here on the left-hand side, on the right-hand side, you have the function's antiderivative, basically, right? So if it's f prime, you're going to observe just an f over here. Now, mathematicians, they like to make things even more general. Instead of f prime, what if you had, just f of x, what I have on the bottom here? If you have just an f of x. And if you've seen this before, please don't give me your answer. I want to have the other students who have never seen calculus to think about this answer. So if on the left-hand side, what I have is f of x, what do you think I'm going to have on the right-hand side? And you can say in words, because there you may not have an equation for it. You can say in words. What would you want to see on the right-hand side? So when you saw f prime up there, f of x showed up on the right-hand side, right? So if you have f of x on the left-hand side, what function do you think will show up on the right-hand side? What is the relationship from f prime to f? The antiderivative, right? So when you have f of x on the left-hand side, you're looking for what then? You're looking for the antiderivative of what? Of f of x. And we usually represent it by capital letter F. So the antiderivative of f of x, which is capital F of x, will show on the right-hand side. And first, you're going to plug in, again, 3 minus, you're going to plug in the lower limit, 1. Again, where capital F represents the antiderivative of lowercase f of x. So, but the general idea is this. If you were integrating, or I shouldn't use that word, if you were finding area under velocity, or s prime, here you end up with s, right? So if you're trying to find area under f of x, you should end up with the antiderivative of the f of x function. And voila, we have our famous fundamental theorem of calculus, which we've just did it together, we derived it together. I should say it's not a real rigorous derivation we did, but we just tried to understand where this formula comes from, this famous theorem. So it says basically that if you're trying to find the area from a to b of a function f of x dx, all you have to do is find the antiderivative of the function and evaluate it only at 2 points. This is like magic. You don't have to know the function in between a and b. You just have to know it at the 2 endpoints. So you plug the upper limit first into your antiderivative minus the lower limit. This will give you the area under that curve. Now, it looks very suspicious, right? It looks too easy to be true. Let's check a few things that we've already done, see how it works, with things that we already know the answers to. For example, we've already done x squared in this class, right? And what was the answer? We did it in our last class. The area under x squared should be what? 1/3. I also have it on the board for you over there, right? Now, let's do it with the shortcut method, see how easy it will be. OK, to find the area under x squared, we need to first find the antiderivative of x squared. What is the antiderivative of x squared? X to the third over 3. And the notation we use is we put a line here saying that we're going to evaluate this from 0 to 1. And based on the fundamental theorem we have just seen, which number are you going to plug in first? Let's go back to the theorem, look at it. You always plug in the upper number first. You see, f of b goes first. So plug in the upper limit first into this antiderivative function. You'll get 1 over 3 minus, so this is your f of b, minus, go ahead and plug in the lower limit now, 0. 0 over 3 is 0, of course. So what do we get? 1/3. Amazing. You could have done it in your head. It could take you probably like 1 second to do it, right? As compared to like, maybe 15 minutes to develop that idea last time, even maybe half an hour. So things are much easier with the fundamental theorem. And I guess that's why it is called the fundamental theorem, because it takes something so difficult or tedious and changes it into something so simple and easy to evaluate. Now, we've already done x cubed in your group activity, right? And we went over it earlier today. On the board. So what was the answer to this one? When we did it a long way, the answer was, look over there, it's on the board. The answer was 1/4, right? Now let's do it with the fundamental theorem. Again, that took us a long time to do, right? It was tedious. OK, find the antiderivative of x cubed, x to the 4 over 4, and substitute the limits. Always plug in the upper limit first. That's your f of b. So you're going to get 1 to the 4 over 4 is 1/4. Then substitute the lower limits. And that gives us 0. So the answer is 1/4. Once again, a very tedious problem turned into something very, very simple. But it is important, I think, to know what's going on behind, this. It's also known as the integration symbol, the elongated S. What's going on in this process? Again, there's a lot of theory behind a simple shortcut rule. And the theory relies on what we saw last class, which is basically Riemann sums, the infinite summation limit as n goes to infinity. OK, before we do this example I have on the board, I want to do that other one we did at the beginning of this class and last class, the integral of x squared, let me do that one, x squared, and the limits were from 1 to 3. And the answer we had gotten earlier, that was a lot of work. We got 26/3, remember? OK, let's check this one right now with the fundamental theorem. OK, first thing we're going to do is take the antiderivative of the function x squared, which is exactly x to the 3rd over 3. And then we're going to plug in the limits we're going to go from 1 to 3. And we start with the upper limit always, because the theorem says f of b minus f of a. So this number is a, this number is your b. So first let's do f of b. So plug in 3 in there for x. You get 3 to the 3rd over 3, right? Minus, plug in the lower limit now for x. You get 1/3. Simplify. Did we get the same answer? We sure did in like 5 seconds. Right. So the method, the fundamental theorem really makes our life easier. However, this too will get messier because, of course, the math books, we take an idea, we beat it to death. We give you all sorts of examples you can possibly see on it. So you will see very complicated functions now, not just an x squared, but maybe 5x cubed minus root x plus 17x squared, something like that. So this too can get a little bit messy, but still, it makes the other process much, much easier. Let's do the one I also have here written in black ink. Integral from 2 to 5 of x squared plus 2. Let's do that one as well. Okay, I'll give you a minute to do this one. So we first take the antiderivative, right? And the antiderivative of 2x, 2 is 2x. Then we plug in the limits. Always we plug in the upper limit first, right? Minus the lower limit. And the way I'm going to combine them, I'm going to first combine the whole numbers. Right, that was a plus 4. So to combine the whole numbers, I have 10 minus 4, that's 6. And then I'm going to combine the fractions together. Let's 8 thirds. That's like 1/17 thirds plus 18 thirds. It's like 135 thirds, I believe. And I think this one actually turns out to be a whole number. I think it goes into, is it 45 times? Yeah, 45 times. So the answer is the area under this curve from 2 to 5 is going to be equal to 45. Okay. Any questions so far about the fundamental theorem? Any questions? Okay. Yes? This is the limit. If you were to do it the long way, first you would do like a sub n using like n rectangles. You use summations to simplify. Then you take a limit. At the end of all of that, you would get 45. So in a sense, you have now a powerful tool to check your answer. So you can go back to the last section. Many questions you were maybe struggling with it there. At least now you know what the right answer is because you can integrate it, get the right answer. Now, if I say find the area using 20 rectangles, it's not going to be exactly 45, but it shouldn't be like 75. So it should be something in the vicinity of 45. Maybe you get 40 or 47 or something. Because if you had 20 rectangles instead of using infinitely many rectangles, but still, you should be in the ballpark of the exact answer. So this is a great tool also to check the answers from the last section. Yes?
So is this from the left or the right side?
Basically, it doesn't matter. Whether you approach from the left side or the right side, ultimately, the limits all converge to a unique number. Because as you have lots and lots of little rectangles under a curve, you see the overflows and underflows are like disappearing completely. You could take the right endpoint, you could take the left endpoint, you could take the midpoint. And actually, there's a theorem that says you can take any point in that interval. And that's actually the real definition of a Riemann sum. Any point in the interval, where you have the base of that rectangle, not just the left side, not just the right side, but you will still have the same exact area. Because in the limiting case, no matter what point you select for your height, it's going to, those overflows and underflows, as you have many, many rectangles, they disappear. You have like tiny, tiny ones. So it doesn't really matter which point you get. Okay, let's do another example. Actually, this one I want to explain to you a rule, and then after that we're going to do examples about that rule. So what if you have a situation where the function is not always positive? So far we've restricted ourselves to situations where the function is positive. So like this function right here. It oscillates. First it's positive, then it's negative, then it's positive again. How do you find the total area between the function and the x-axis? And the answer is pretty simple, actually. You go in bits and pieces. Like first you go from A to B, then you go from B to C and C to D. In each case, you find the integral. You apply the fundamental theorem. But when you are dealing with this side where you have a function below the x-axis, just remember to take the absolute value. So this is the rule. As you can see, from B to C, I took the absolute value of the function because it was below the x-axis. It was negative in that region. So from now on, since we are not restricting ourselves to just positive functions, you guys have to be very careful from now on, okay? When I say find the area between the function and the x-axis, the first thing we must do from now on is we must graph it, because you need to know, is it always positive? Does it go below the x-axis at any time? Second, you must find the x-intercepts. If it goes below the x-axis, you must find all the x-intercepts, and then you integrate over each of those intervals where it's positive and where it's negative. And don't forget at the end to add the absolute value of all the answers. Obviously, the positive ones, you don't have to take absolute value, but the negative ones, you must. Okay, if you guys copied it, then I'm going to go ahead and give you another example then about finding area. Let's find the area between f of x equals x squared minus 2x over the interval from 0 to 5. Find the area between f of x equals x squared minus 2x over the interval from 0 to 5. So the moment from now on you hear the word area, you must graph the function, because we're no longer restricting ourselves to positive functions. You need to know, is it always positive, negative, or somewhere in between? So we must graph this function first. And this one should not be a hard one to graph, because first of all, it's a quadratic function, right? It opens up or down? Up, because x squared is positive. What are the x-intercepts of this function? If you set equal to 0, you get x times x minus 2. 0 and 2 are the x-intercepts. So already we have a pretty good idea about what 0 and 2 are the x-intercepts. So it opens upwards. So roughly speaking, this is what the graph looks like. And we want to find the area from 0 to 5. So let's shade what that region looks like. So it will consist of the union of two separate regions, right? It's going to be the union of this region plus this region. Okay, how will we set it up? Can I go in one shot? I can say integrate from 0 to 5. No, that will give you the wrong answer, because you have some negative area there that would take away some of the area from the other one. You would not be getting the correct area. So the way to set this up is, first, let's say a sub 1, the first area will be the absolute value of which integral? 0 to, right, the intersection point there is 2. So integrate from 0 to 2 of f of x dx. In other words, x squared minus 2x dx. Basically, whatever the answer turns out to be, at the very end, take the absolute value. Don't take absolute value in the intermediate process, but finish this integration. You're going to get a negative answer, and you must get a negative answer because you see the region is negative, and then make sure you make it into positive. Okay? Then integrate find the second area, a sub 2, which will be the integral of, from where to where? 2 to 5 of the function f of x dx, which is x squared minus 2x dx. Once again, same function. And that you expect to get a positive answer. At the end, we're going to add the 2. I'll give you a little bit of time to work on this. But just this notation dx, by the way, it's kind of like symbolic, right? It's really not doing anything. When you take an antiderivative, that dx is really not doing anything, right? But why is it there? It's like symbolic of the, where it's coming from. Remember summation f of x by delta x, the dx is representing the base of the rectangles. But here it's really not doing anything with the shortcut method. It's just there to remind us where everything came from, basically. Okay, I'll give you a little bit of time on this. So once again, we take the antiderivative, of course, plug in the upper limit minus the lower limits. So if I plug in 2, I get 8/3. Minus 4. Plug in 0, I get 0. And that's the same as 8/3 minus 12/3. So I'm getting negative 4/3, which is to be expected, right? First, the integral was negative, but the area of that first region is going to be the absolute value of that answer, which is positive 4/3. Right? Then let's find the second area. That one was from 2 to 5 of the same function. Again, first I write the antiderivative. And the limits are going to be from 2 to 5. Now, just a little important, I want to point out something with regard to the notation. Many times when I'm grading students' papers, students find the antiderivative, and after they find the antiderivative, they keep their the integration notation there. This would be wrong. This is kind of like saying, you took the square root of 4, you got a 2, but at the end you kept your square sign still there. That's completely incorrect, right? So once you take your antiderivative, you should not have the integral symbol there anymore. Okay, you can put the line there to represent. We're going to evaluate it, but the integral sign has done its job. You found the antiderivative. It should disappear at that next level. Okay, so now let's plug in the upper limit, 5. And then minus the lower limit of 2. And once again, I'm going to combine the fractions first. So that's 1/25 minus 8/3. And then the whole numbers are negative 25. And negative times negative is positive 4. So that's 1/17 minus 21. And again, getting common denominators. So I get 117 minus 63 over 3. And for that, I got 54/3. So what should be the final answer? Right, I'm going to keep it like that because I know I'm going to be adding it to the other one. So one part was 4/3, the other one was 54/3. So I'm going to add the two together. So 54/3. Oops, not 13ths, but thirds, plus 4/3 is indeed 58/3. It's not writing so well. There we go. Okay. So this is the total area enclosed between the graph and the x-axis over the given region. Yes, Daniel?
Now, would you always add the two areas, or would you ever be subtracting it all?
If the question says find the total shaded area, you should take the absolute values of each of the separate areas and you should always be adding them.
So you never have a negative?
If the question uses the word area, now we're going to do some examples where you're going to see, but if the question says area, you should always take absolute value, you should always add. Okay, I'm going to give you one more example about area, and it's on the bottom of this page. Okay. This question, you don't have a specific function. Like, I don't know if it's f of x squared or x cubed, I don't know. All I have is I have a graph. So you can see first it's positive, then it's negative, then it's positive again. And they gave us the integral values over those three regions. From A to B, it's 2. B to C, it's -5. C to D, it's 6. They gave us the integral values. And there are two questions to be answered. One is, what is the total shaded area? And the other one is, what is the total integral? The integral for a positive function gives you the area, right? For a negative function, it gives you -1 times the area. So what will it be? What will be the total shaded area? So there you add the absolute values, right? So 2 plus absolute value of -5 plus 6. So you are correct in that regard. So here it should be 2 plus absolute value of -5 plus 6. So that is 13. And then the question says, what is the integral from A to D, from the first point to the last point, of the integral of the function? Now this is not referring to the area at all. It's just saying what's the total integral. And there is actually a property that says, like, if you're going from, let's say, from A to D, you can add up the integral from A to B, to the integral from B to C, to the integral from C to D, and that will give you the integral from A, from the original point to the last point. So that one, guess what that one will be? 2, right there you don't take any absolute values. And that one turns out to be 3. So if the question says area, you should always be adding absolute values. If the question just a practice problem on what is called integration, then you have to keep all the signs as they are, like we did in this case. As a matter of fact, some of the next few examples we're going to be doing, we're going to be practicing integration in general, not just area, because integration has many more applications besides area. So that's what we're going to be doing next. So one more area question, and then we're going to go to something a little bit different. This one is a little bit unusual in that it's not area under the curve, right? This time they are asking the area above the curve. So how do we deal with that? I want to give you some time to think about it, and then we'll go from there. First, I want to do some brainstorming. Any thoughts how we could approach this question, how we could find that shaded area? Yes, Sandra? Which is going to be base times height, right? I think that would work perfectly, don't you think? Because if you find the integral of that function from 0 to 1, that gives the area under the curve, right? We can find the total area of the rectangle, subtract it, and you can find the area above the curve, right? By the way, I don't really need to tell you even the height there. And some of the group activity questions, I did not give you the height. How could you have obtained the height if I did not give it to you? If I gave you x equals 1, you would just plug it into the function, right? So 1 squared plus 2 would be 3. That would be your height. Okay, so let's do just that. To find the area above the curve, first we're going to find the area under the curve. So I should go from 0 to 1, right, of the function x squared plus 2. Okay. So then we integrate. And then we plug in the values. So I'm getting 7/3 for the area under the curve. And to finish it off, area shaded equals the big area, as Sandra suggested, 3 times 1, the area of the rectangle, minus the area under the curve, and that gives us 2/3. How do we know the area of what? I'm sorry? Yes, the area of the shaded region will be the area of the big rectangle minus the area of... Yeah, oh yeah, 3 is the length times base, length times height. The length times width. The width is 1, the height is 3, so we multiplied. Right, because this distance was 1 unit, right? And this distance was 3 units. So we multiply the 2 dimensions to find the area of the rectangle. And remember, if I did not give you the number 3, you should be able to determine that yourself. And how do you determine it? By plugging 1 into the function, right? Okay. Okay. Now, a few examples on practicing problems with definite integrals. In other words, these questions, they're not asking you to find the area. These are just practice problems on evaluating what is called definite integral, meaning an integral that where you have limits of integration, like you're going from 0 to pi or any number of values given. If the question does not say find the area, you do not have to graph it. And the answer can be negative, we don't care. The only time we care is if the question says find the area, okay? Otherwise, it's just a practice problem on the integration process. So the first one is asking, what is the integral of 1 plus cosine x dx from 0 to pi? So what is the antiderivative of 1? Of course, that's x. Antiderivative of cosine x is positive sine x, right? In their differentiation, it was negative. In anti-differentiation, it is positive. And we're going to go from 0 to pi. And, of course, plug in the limits. First, the upper limit minus the lower limit. Okay, what do we know about sine of pi? So sine of pi is 0, right? Because sine is 1 up here, negative 1 down here. It's 0 here and here, right? So sine of pi is 0. So we're going to get pi plus 0. And sine of 0 is 0 as well. So everything else disappears. So the answer is just pi. What about the next one? The integral of 4 secant u times tangent u. First things first, the antiderivative. It's just secant, right? But there's a 4, so it's going to be 4 times secant of u. How do I know this? Because the derivative of secant was secant times tangent, right? So the antiderivative of secant tangent is secant. And the limits are from 0 to pi over 3. Now, when you have a constant, you can factor it outside if you like. And you can write it like this. 4 times secant of pi over 3 minus secant of 0. Now, pi over 3 is 60 degrees. What is cosine of 60 degrees, first of all? Cosine 60 is the same as sine 30, which is 1/2. So secant of 60 degrees will be 2. So here we're going to have 4 times 2 minus, what about cosine of 0? Cosine of 0 is 1, so secant of 0 is 1 as well. So we're going to have 4 times 1. In other words, the answer will be 4. Okay, one more. Okay, the integral of secant squared t dt, 3 times secant squared from 0 to pi over 4. Once again, what is the antiderivative of this function? Again, think of a function whose derivative is secant squared, right? Which is the tangent, exactly, the tangent function. And we're going to go from 0 to pi over 4. Pi over 4 is 45 degrees. What do we know about tangent of 45 degrees? That's 1. And tangent of 0 is 0. So the answer will be 3 times 1, or 3. Okay, I want to give you one more. Okay, let's do this one. Find the integral from 1 to 4 of negative x squared plus 2x minus root x plus 1 dx. It's going to be a little bit messy. And let's see what you're getting there. Okay, so I took my antiderivative, I plug upper limit minus lower limit. And again, I'm going to collect my whole numbers together and then the fractions, and then at the end combine them all together. So I'm going to combine 16 plus 4, which is 20, minus 2, which is 18. And then the fractions, I've got negative 64 thirds, minus 16 thirds, and then, pardon me? Yes, how do we integrate root x? Yes, root x is the same as x to the 1/2. Right, right. But I'm going to show it down here because I have more room down here. Right. So root x is the same as x to the 1/2, right? Its antiderivative is we add 1 to the power, gives us x to the 3/2, and we divide by that power. Dividing by 3/2 is the same as multiplying by 2/3. So that's how we got that term. So when I was combining my numbers on the bottom, I took the whole numbers first, and then the fractions. Now this gave me 3 over 3 or 1. So I'm going to combine it with my whole number. 18 plus 1 will be 19. Did I miss that? No, no, no. The 18, look at my red check marks. I had 16 plus 4 was 20, and minus 2 was 18. That's how I got my 18. Again, there are many, many ways to do this. You know, maybe you do everything in the first parentheses first, if you prefer. Do everything in the second parentheses, and then just do one subtraction. Obviously, you can use a calculator if you want to. You can also do that. So again, do it any way that is more convenient for you. So now I'm combining negative 64 minus 16. That's going to be negative 80 thirds. And then finally, I get common denominators here, 3 over 3. And that's, I believe, 57 minus 80 over 3. So that's like 23 thirds, but it's negative. How many of you, again, no matter which way you selected, how many of you got the same answer? Good, and some of you are still working on it, which is perfectly fine. As you can see, it can get a little bit messy, and you just do lots of practice to get all the the little details out of your all the possible places you can make mistakes. The biggest problem usually is this negative sign right here. Make sure you distribute that negative sign very carefully to all the terms after it, or like I said earlier, do everything in one parenthesis, do everything in the other, and simply combine them with one subtraction, of course, by using the calculator. And let me end today's lesson by showing you a nice shortcut method on the calculator, a way you can check your answers. But obviously, since I'm showing you this, I'm going to want to see all the work, but you can check your answers this way. There is a function integration key in your calculator. It's under the math menu. So go to math and go all the way down to find the function integration key. So go to math. You can go all the way down or go up where it says FNINT. It's number 9 on my calculator, as you can see, FNINT, function integration. And the commands it takes are the function you're integrating. Let's do something really simple, like the x squared function, right? So just put the function you're integrating. So you're integrating x squared, comma the variable x, comma the limits from where to where you're going. Let's say we're going from 0 to 1. And what do we get this answer to be? We can do this in our head now, right? What is the antiderivative of x squared? X cubed over 3 from 0 to 1. The answer should be what? 1/3, right? Let's see. Press enter. There we have it. It gives you a numerical format instead of the fraction format. But again, it's a great way to check your answer, go back if you didn't get the same answer by hand, debug your solution, find where you made that mistake. But obviously, I'm going to need to see every single work. And now I'm even more careful so to check the work because I know the calculator can give you the final answer there.